we continue our discussion on clustering and classification of data. And in the last lecture, we discussed various algorithms for clustering of data points. And in this lecture, I will start discussing on different classification approaches. Now, classification is the task of assigning a known category or class to an object. There are various approaches. Out of them, a few are shown here. It could be probabilistic approach, distance based, discriminant analysis based approach. You can use also artificial neural network for classifying data points. In this lecture or in this particular topic under this course, I will be considering a few examples of each of these approaches. There, for the probabilistic approach, we will be considering Bayesian classification techniques. Particularly, we will discuss about naive based Bayesian classifier. For distance based approach, we will consider K nearest neighbor classifier, and discriminant analysis we will discuss about linear discriminant analysis. And then in artificial neural network, it is a feed forward neural network that we will be discussing. So, let us start with the problem definition of a classification task. Here you have a labeled data sets given in the form of yi, xi. Note here, xi is the data point. This is a n dimensional vectors. As you know, for every object in an abstract way, they are represented as a feature vector in a n dimensional real space. So, xi is such a vector or such a point in a real dimensional in a n dimensional real space, and yi is its class. It could be any categorical data, it could be some names of class, or there could be numeric representations of those classes. So, the numeric values distinctly identify these classes. However, so we consider of course a finite set of classes. So, it is an element of a finite set of classes, and we can design a classifier C. I mean, that is the problem statement, that we need to design a classifier C which assigns class yi to xi. So, which should be supported by which should support this data set. So, as I mentioned that for a two class problem, say yi could be denoted as +1 or -1. There is a risk associated with classification, particularly misclassification, as you can see that risk is defined as the number of misclassified data, and it is the fraction of number of misclassified data. That is how the risk is defined. And incidentally, Bayesian classification, which we are going to discuss next, it minimizes this risk. So, let us consider this particular thing, that Bayesian classification. So, it is the name comes from the the theoretical framework which has been proposed by Bayes, and there is a Bayes theorem. We will discuss about this theorem from which this classification rules are set and classifiers are designed. It is a probabilistic prediction of belongingness to a class, and a simple Bayesian classifier, that is an example of a simple Bayesian classifier, is the naive Bayesian classifier, which we will be considering in particular in this lecture. Each training example in this case, it can increase or decrease the probability of the predicted class. So, incrementally you can learn the classifier. That is the advantage of this classification technique, and prior knowledge can be combined with observed data. So, let us consider the Bayes theorem and the inferencing that could be carried out using by applying this theorem. So, first we know the definition of a conditional probability. It is from the joint probability of A and B. We can say either B occurs given A or A occurs given B. So, probability of A and B could be expressed as probability of A multiplied by probability of B given A, or probability of B into probability of A given B. So, they are all equivalent they should give you the same probability value. Now, Bayes' theorem is derived from this observation that you can see that it has been shown that probability of a hypothesis H given a data x can be expressed as the ratio of these two quantity. In the numerator is the joint probability of H and x, and which are expanded in the form of probability of H and probability of x given H, and in the denominator it is the probability of x. So, probability of H is the prior probability of the hypothesis based on our previous knowledge, whereas probability of x given H we call it a likelihood function. So, in the particular hypothesis, if it is true, what is the likelihood that x will occur under this hypothesis, and probability of x is the unconditional probability of data. So, it is a normalizing constant in this particular case, which is ensuring posterior probability sum should be 1. That means, if x occurs, there could be all different hypotheses which may generate this x. So, which are those hypotheses from which this occurrence of this x belongs to or conditional. Now, if I sum all those possibilities, that should be equal to probability of x. So, posterior probability of the hypothesis or assigning a given the data. So, given training data x, posterior probability of a hypothesis H, it can be computed by following this Bayes theorem. We will see that it has significance, it has relevance in terms of designing a classifier, because here our objective is to maximize the probability of a class given the data, and class is representing an hypothesis. So, we need to compute this posterior probability there. So, that is what is the Bayesian classification rule or Bayes classification rule. It says that assign C I to x if and only if the probability of C I given x is the highest among all the other classes, all other probabilities for all other classes. So, there are challenges of course in this computation. It requires prior knowledge of probabilities of classes and their distributions in multidimensional feature space. So, just to once again summarize the problem statement in a more concrete form, we have an input to our classifier. It is a training set of tuples and their associated class levels, and each tuple is represented by an n-dimensional attribute vector x. You have shown the name of the attributes, or the representation has been shown here, and they are the data points what I am referring in an n-dimensional space. And let us consider there are m classes. So, as we discussed in the previous slide itself, our objective is to derive the maximum posteriori probabilities. So, for a class, the class which gives the maximum posteriori probability given the data. So, that class should be assigned to data. So, we can compute this posterior probability using Bayes theorem of conditional, using the conditional probability rule, that you can compute the prior of class C I. So, this is the prior probability. Now, this computation can be, you can get it from the data point itself. Some a priori information can be obtained from other knowledge from a different source. But given the data distributions among different classes, we can compute that how many times for a data occur in a class. How many times class instances are occurring among all the classes. So, that fraction can estimate this prior, and by observing the data distribution within the class itself, we can compute this probability density function or probability of x given C I also. So, this is called likelihood. So, this term is likelihood, and you can see this numerator probability of x actually you did not compute, because while comparing the values of probability of C I given x or posterior probabilities, this numerator is constant given the data x, this numerator is constant for every classes. So, it is sufficient this denominator is constant for every class, this is the probability of x. So, it is sufficient if I compute just the numerator part or compute these two quantities, that would give me the probability, that would give me the basis of comparison. I am not in absolute sense computing the posterior probability, but in relatively I can compare them by computing those factors. So, this is what that is a summary. Only product of probability of C I and probability of x given C I needs to be maximized. That is a problem statement. So, now we will be discussing about naive Bayes classifier. It works on a simplified assumption where attributes are conditionally independent, which means that there is no dependence relation between attributes, and in that if it is true, then you can write the likelihood of x given a class C I as the product of all likelihood probabilities of individual attributes, because attributes are independent. So, that is the advantage simply you can compute this probability. So, all likelihood functions can be defined in one dimension instead of a multidimensional representation of probability density function. That is the simplicity of naive Bayes classifier. Your handling of data becomes simpler, or handling of multidimensional data becomes simpler for modeling the probability density function. So, there is a significant reduction of the computation cost because of this, and it requires only the class distributions, and that too in a single dimensional feature space. So, it is convenient to estimate every attribute probability of every attribute given a particular class. And for example, for a categorical or discrete variables, you can count how many times that values of attributes have occurred given all the occurrences, all other values of those attributes, and then you can find out the fraction of its occurrences over all occurrences, and that can give an estimate of this probability. Or if it is a continuous variable, then you can model it by any continuous probability density function. Any kind of parametric modeling of density functions you can do. For example, Gaussian distributions you can do, and from there by estimating the parameters of Gaussian distributions, you can compute this probability. So, you know that in Gaussian distributions there are only two parameters for a single dimensional, one dimensional feature space. You have only its mean and standard deviation there. So, the likelihood is expressed in this form as we mentioned, and we need to estimate the probability of a given attribute x I for given the class. So, there is a class conditional probability of an attribute x I, and as just I mentioned that these are the methods by which you can do it. Here this is just elaborating that how parametric modeling of Gaussian distribution could be done in the one dimensional feature space. So, this is the distribution, this is the probability density function of a variable x, one dimensional random variable x which follows a Gaussian distribution, and you can see there are two parameters here. One parameter is mu, which is called expectation of this distribution, or we can in a simple layman's term we can call it mean, and this is sigma which is actually the standard deviation of these distributions. So, given the data you can always estimate these values from mean and standard deviations. These parameters could be estimated, and so this is what you are considering for it is a product of all these things which has been in this case actually I should write it in this way. This is probability of g x I mu I sigma I equal to 1 to n. So, this is what is the probability of this variable n dimensional feature given the class C I. This is how it should be written. So, there is some problem with this particular expression. So, let me consider an example to explain, to elaborate these computations. You can see this example here, and here there is a data set which has been shown in this particular example. In this data set, you have the statistics of the computer buyers. I mean, whether a person buys a computer or not, you have that kind of statistics. The person's age has been shown here, then the income, and whether the person is a student, and what is the credit rating, and whether with that background, whether that person particularly has bought a computer or not. So there are few distinct values for each variable. So these are the attributes: age, income, student, credit rating, and computer buyers. So these are the attributes, and computer buying is the class. You can see there are two classes. One buys computer, where the value would be yes, and the other class buys computer, the value is no. And here the problem here is that we need a data when a person has this kind of attributes or data associated with a person. What is the probability that the person buys a computer, or rather not only probability, actually in which class category we can put this person, that whether this person should be in the class of buys computer or not. So this is what is this particular classification problem. So first we need to compute the class prior in this case, and you can see that here I have shown with color that how many instances of computer a person buying a computer is there, and how many instances a person not buying a computer is there. So these are the instances which in which cases a person did not buy a computer. So there are 2 to 4, there are 5 such instances of no. And if I count this number of records, there are actually 14, which means 9 instances there for yes. So that is why the probability of prior probability of a class of buys computer equal yes would be 9 by 14. That is a fraction. That is how this probability is considered. And similarly, the probability for the other class would be then 5 by 14. Okay. So these are the two prior probabilities that we have estimated from this data. Then we will we will compute the likelihood for each attribute value for each class. So now we will consider the likelihood of age given the class buying computer and also the not buying computer. So there what we need to consider here, that for each class we have to see the distribution of distribution of the attribute values. That means how many times, what is the fraction of times age less equals 30 occurs out of all possible values of attribute of age. So if I consider say no, we will see that this is one occurrences of this fraction. This is also another occurrences of this fraction. This is not for class no, this is for yes. So there are 4 times this age less equals 30 occurs, and actual occurrences of no is 5. So the class likelihood probability of age less equals 30 is quite high here. It should be 4 by 5. Whereas the other cases, when the class of yes, there we can see that there are so many instances, 1, 2, 3, that means out of 9 cases only 1 instance of buying age. So this is for yes is there out of 9. So which means its likelihood probability is 1 by 9. So that is how we can compute these probabilities. So this is yes and this is yes. So that 4, it was actually 3, it is not 1 is reduced. So yes has 2, so 2 by 9 instead of 1 by 9, because 1 I mistook, I considered that was in the class no. So it is 2 by 9, that correction should be there for this data, 2 by 9 for yes and 3 by 5 for no. So, the probability is a 0.222 likelihood probability given the class yes and 0.6 given the class no. So, let us proceed again for the other cases. So, now we are considering the income equals medium. Once again we will see how many times medium has occurred. So, 1, 2, 3, here actually I have given color. So, from the color we can find out for no, medium has occurred twice for no, and we know that for the class no, that means the persons, though they are not buying a computer, there are 5 instances. So, the likelihood probability should be 2 by 5, that is the probability of this attribute given the class no, in short if I write. And for yes, again it has occurred. So, this is yes. So, 2, 3, 4 times. So, out of 9 instances of yes, 4 instances were of income medium. So, it should be 4 by 9. So, that is the value. Let us check once again whether I made mistake in this case also. Let us see. Yes, 4 by 9 and 2 by 5. So, these are the values, these are the likelihood values. We will proceed further. This time it is student equals yes. So, which means the person is a student or the person is not a student here. So, here we observe that for one instances in the class no, it is a student, and which means that likelihood probability given the class no, means not buying computer, for a person is a student is 1 by 5. So, this is probability yes, let me write it in short. This yes meant this is for student and this is for class. So, this is 1 by 5, and the other cases we have shown that how many times student has occurred. That means, persons who have bought computer, how many of them are student, or there are 9 persons who have bought computers in this data. Out of them, this is one, this is another, this is another, this is another, quite a few. So, it is 6 by 9. So, probability the student yes given the class yes. So, 6 by 9. So, let us see once again. Yeah. So, this is how the likelihood of student equals yes, that attribute value given the classes could be computed. So, the next attribute we will be considering credit rating, where the given the data we have credit rating equals fair. So, in this case we have these are the instances when persons are not buying computer, they have this attribute value of fair credit rating, which means that you will have 2 by 5 when it is fair given the class no, and for yes you have 3, 4, 5, 6. So, 6. So, that is 6 by 9, that is a credit rating fair given persons buys a computer. So, these are the values that we can estimate, likelihood estimates, right. So, you have 6 by 9 by 2 by 5. So, we have computed all the likelihood values of age less equals 30, income equals medium, student equals yes, and credit rating equals fair. So, the likelihood of x given any class, any particular class Ci, for example, the class could be person buying computer, means it is the product of likelihood of all those given classes. So, we can compute in this way finally, likelihood of this data given these two classes can be computed. We can find out that the value is 0.044 when the class is yes, that is buying a computer, and value is 0.019 when the class is buys a computer, it's no. And then finally, the posterior has to be computed, which means each likelihood has to be multiplied with their prior, and then you get the posterior, I mean proportional value, of course. We are not dividing with probability of x. It is not the absolute posterior value, but we can get the proportional posterior value. So, this is how we are getting. So, in this case, it is not exactly this, it is proportional in particular this constant when x is given, it is a proportional value. So, the posterior of this, I should say once again, this is this is the product of these two, that is 0.028. So, this value is 0.028 and the other value is 0.007. So, naturally 0.028 is the greater value, and this is out of these two classes, this is the maximum. So, which means that I can assign this this variable to a class of computer buying class. So, that is the inferencing. So, therefore, x belongs to class of buys computer equals yes. So, this is the example of learning. So, one of the problem of the computations of this likelihood is that if there is any zero probability, suppose there is no instance at all, it may happen in your data point for a particular class, then the likelihood becomes 0. So, or very small that is one of the problem. So, to avoid this we need to do certain, because it is a observations and observations are noisy. So, we do not expect that it would be absolutely 0 for every class the likelihood. So, but it is low, it indicates it should be low. So, in that case, so this is one example that data set with 1000 tuple, income equal to low 0, income equal to medium 990 and income equal to high 10. So, we use a correction which is called Laplacian correction or Laplacian estimator by adding 1 to each case. So, instead of 0, we consider the value is 1. So, we get a very low probability and we avoid this problem of 0 probability in computing likelihood. So, what are the pros and cons of naive Bayes classifier? The advantage is that it is easy to implement, good results obtained in most of the cases. There are disadvantages, like first it is a assumption is that class conditional independence, which may not be true for a realistic data, and if it is not true, then there will be loss of accuracy. So, that is what in real life dependencies exist among those attributes or variables. For example, hospitals, patients, profile, age, family history, etc., symptoms, fever, cough, etc., disease, lung cancer, diabetes. So, many of the informations are related, and this cannot be modeled by naive Bayes classifier. So, let me take a break here. We will continue this discussion of different approaches of classification in the lectures. So, thank you very much for your listening.